Imagine staring at a perfectly smooth wall, painted with the most uniform coat of paint you've ever seen. Now, imagine discovering a single patch on that wall that's inexplicably different, a spot so anomalous that it challenges everything you thought you knew about how that wall was painted. This isn't just a metaphor. Deep in the cosmos, astronomers have found exactly such a spot, a cosmic anomaly so profound that it might be evidence of something that should be impossible. Another universe entirely, pressing against our own reality like a fingerprint left by a neighbor we've never met. This mysterious region, known as the cold spot, sits in the constellation Eridanus, covering an area of space roughly equivalent to 1 billion light-years across. To put that into perspective, if our entire observable universe were the size of Earth, this cold spot would be larger than Asia. Within this vast region, the cosmic microwave background radiation, the afterglow of the Big Bang itself, appears significantly colder than anywhere else in the universe. It's as if someone took a cosmic eraser and partially rubbed out a section of creation's blueprint. But here's what makes this discovery truly extraordinary. According to our best understanding of physics and cosmology, this cold spot shouldn't exist. The universe, as we observe it, should be far more uniform than what we're seeing. The very presence of this anomaly suggests that either our fundamental understanding of the cosmos is incomplete, or we're witnessing evidence of something that exists beyond our universe entirely. Today, we're going to journey into one of the most profound mysteries in modern astronomy, a puzzle that might rewrite our understanding of reality itself. The story begins with something that surrounds us at every moment but remains invisible to our eyes: the cosmic microwave background radiation, or CMB. Picture the universe as a vast ocean, and the CMB as the gentle, persistent waves that ripple across its surface. This radiation is the stretched and cooled remnant of the incredibly hot, dense state that followed the Big Bang. When the universe was only about 380,000 years old, it had cooled enough for the first atoms to form, allowing light to travel freely through space for the first time. That light, now stretched by 13.8 billion years of cosmic expansion, reaches us today as microwave radiation. What makes the CMB so remarkable is its uniformity. No matter which direction you look in the sky, the temperature of this ancient light varies by less than 1 part in 100,000. It's like measuring the temperature of every grain of sand on a beach and finding that they all differ by less than a fraction of a degree. This incredible uniformity was one of the great confirmations of the Big Bang theory, but it also presented cosmologists with a puzzle known as the horizon problem. Think about it this way. Imagine you're at a massive concert, and somehow, despite being in different sections with no way to communicate, every single person in the audience is wearing exactly the same shade of blue shirt. How could regions of the universe that have never been in contact with each other exhibit such remarkable similarity in temperature? The answer, cosmologists believe, lies in a period called cosmic inflation, a brief epoch immediately after the Big Bang when space itself expanded faster than the speed of light, stretching quantum fluctuations across the observable universe and creating the nearly uniform cosmos we see today. But here's where our story takes its first surprising turn. While the CMB is remarkably uniform, it's not perfectly uniform. There are tiny temperature fluctuations, typically no more than a few millionths of a degree, scattered across the sky. These minute variations are like the seeds of everything we see today, the gravitational wells that would eventually grow into galaxies, stars, and planets. Most of these fluctuations follow predictable patterns, clustering and organizing in ways that match our theoretical models beautifully. Then there's the cold spot, an anomaly so large and so cold that it defies easy explanation. Discovered in 2004 by astronomers analyzing data from NASA's Wilkinson Microwave Anisotropy probe, this region appears to be about 70 microkelvin colder than the average temperature of the cosmic microwave background. That might not sound like much, but in the context of the CMB's incredible uniformity, it's like finding a snowball in the middle of a perfectly heated room. The cold spot isn't just cold, it's also enormous and surprisingly empty. Follow-up observations using radio telescopes revealed that this region contains far fewer galaxies than would be expected based on the average density of the universe. It's what astronomers call a cosmic void, but one so large and so empty that it pushes the boundaries of what our current models of structure formation can accommodate. To understand why this is so puzzling, we need to delve into the relationship between the CMB and the distribution of matter in the universe. The tiny temperature fluctuations in the cosmic microwave background are directly related to variations in density that existed in the early universe. Regions that appear slightly warmer in the CMB correspond to areas that were slightly denser and would eventually become clusters of galaxies. Regions that appear cooler correspond to areas that were less dense and would become cosmic voids. But the cold spot presents us with a paradox. If it represents a region that was significantly less dense in the early universe, it should have evolved into a cosmic void, which it has. However, the size and depth of both the temperature anomaly and the corresponding void are so extreme that they challenge our understanding of how structures form and evolve in the cosmos. It's like finding a crater on Earth so large that it couldn't have been created by any known type of impact. This brings us to one of the most intriguing aspects of the cold spot mystery, its potential connection to cosmic inflation and the multiverse hypothesis. Cosmic inflation, while solving many problems in cosmology, also leads to some startling implications. If inflation occurred in our universe, theory suggests it should be occurring elsewhere as well, creating an infinite number of bubble universes within an eternally inflating multiverse. Now, here's where the story becomes truly mind-bending. Some cosmologists have proposed that the cold spot might be evidence of a collision between our universe and another bubble universe during the final stages of inflation. Picture two soap bubbles approaching each other in slow motion. Just before they merge or bounce off each other, they would deform, creating a flattened area where they make contact. In the context of the multiverse, such a collision could leave a permanent scar on our cosmic microwave background, a region where the normal patterns of temperature fluctuations are disrupted. This isn't science fiction. It's a hypothesis being seriously considered by leading cosmologists. The mathematics of eternal inflation naturally leads to the possibility of such collisions, and researchers have developed sophisticated models to predict what the signatures of universe collisions might look like in our CMB data. Some of these models suggest that we should see exactly what we observe in the cold spot, a large circular region with unusual temperature properties and associated large-scale structure anomalies. But let's step back and consider the broader context of this discovery. The cold spot was first identified through systematic surveys of the cosmic microwave background, surveys that represent some of the most precise measurements ever made in astronomy. The Wilkinson Microwave Anisotropy Probe, or WMAP, which operated from 2001 to 2010, mapped the temperature variations in the CMB with unprecedented precision. Its successor, the European Space Agency's Planck satellite, pushed these measurements to even greater accuracy between 2009 and 2013. These missions transformed our understanding of the universe. They confirmed that ordinary matter makes up only about 5% of the universe's total energy density, with dark matter accounting for about 27% and dark energy making up the remaining 68%. They precisely measured the age of the universe at 13.8 billion years, and provided exquisite details about the cosmic recipe that governs everything from the formation of the first stars to the ultimate fate of the cosmos. Yet among all these remarkable confirmations of our cosmological models, the cold spot stands out as a persistent anomaly. Multiple independent analyses of both WMAP and Planck data have confirmed its existence and its unusual properties. It's not an instrumental error or a processing artifact. It's a real feature of the cosmos that demands explanation. One of the most compelling aspects of the cold spot mystery is how it connects to fundamental questions about the nature of space and time. If the multiverse hypothesis is correct, then our observable universe represents just one bubble in an infinite foam of realities, each with potentially different physical laws, constants, and structures. The idea that we might be able to observe evidence of these other universes through their gravitational or topological effects on our own reality opens up profound new avenues for empirical research in cosmology. Consider the implications if we could definitively prove that the cold spot represents evidence of another universe. It would mean that the multiverse, long relegated to the realm of theoretical speculation, could be studied through direct observation. We would have our first concrete evidence that reality extends far beyond the boundaries of our observable cosmos, that we are part of a vast community of universes, each as real and complex as our own. But the cold spot hypothesis faces significant challenges. Alternative explanations for the anomaly have been proposed, including the possibility that it results from unusual properties of dark energy or modifications to general relativity on the largest scales. Some researchers have suggested that the cold spot might be explained by a particularly large cosmic void that creates temperature anomalies through the integrated Sachs-Wolf effect, a phenomenon where light from the cosmic microwave background gains or loses energy as it travels through gravitational fields that change over time. The integrated Sachs-Wolf effect works like this. Imagine light from the CMB traveling through a region where matter is less dense than average. As the universe expands, this low-density region becomes even more diluted, and its gravitational field weakens. Light that enters this region when the gravitational field is stronger will gain energy falling into the gravitational well, but it will lose less energy climbing out of the weakened field as it exits. The net result is that the light gains energy, appearing slightly warmer when it reaches us. Conversely, if light travels through a region that becomes more dense over time, it will lose net energy and appear cooler. The cold spot could potentially be explained by such an effect if it corresponds to a region of space that has become significantly more dense than average over cosmic time, perhaps due to unusual dark energy properties or modifications to gravity on the largest scales. However, detailed studies of the cold spot region using multiple observational techniques have struggled to find enough matter to account for the observed temperature anomaly through conventional mechanisms. Radio surveys have revealed that the cold spot does correspond to a cosmic void, but the void appears to be even more empty than would be required to explain the CMB anomaly through known physical processes. This brings us to one of the most fascinating aspects of modern cosmology: the interplay between observation and theory in pushing the boundaries of our understanding. The cold spot represents a perfect example of how unexpected discoveries can challenge our most fundamental assumptions about reality. Just as the discovery of cosmic acceleration in the late 1990s forced us to confront the existence of dark energy, the cold spot anomaly is pushing us to consider possibilities that would have seemed like science fiction just a few decades ago. The process of investigating the cold spot has also highlighted the incredible sophistication of modern observational cosmology. To study this anomaly, researchers have employed techniques ranging from statistical analysis of temperature maps to gravitational lensing studies that trace the distribution of dark matter. They've used radio telescopes to count galaxies in the cold spot region and compared these counts to sophisticated computer simulations of structure formation in the universe. One particularly elegant approach involves studying how the cold spot affects light from more distant objects. Just as a magnifying glass can bend light to create distortions, the gravitational field associated with the cold spot should create subtle distortions in the shapes of background galaxies. By carefully measuring these distortions, astronomers can map the distribution of both ordinary and dark matter in the cold spot region, providing crucial tests of different theoretical explanations. These observations have revealed something remarkable. The cold spot appears to be associated with one of the largest known structures in the universe, a supervoid that spans roughly 1 billion light-years across. This supervoid contains about 20% less matter than would be expected based on the average density of the universe, making it one of the most underdense regions ever discovered. The existence of such large voids presents its own cosmological puzzles. According to our understanding of structure formation, matter in the early universe was distributed in a nearly uniform pattern with only tiny density fluctuations that would grow over time through gravitational attraction. These fluctuations should have grown in a predictable way, creating a cosmic web of filaments, clusters, and voids, but with characteristic size scales determined by the physics of the early universe. The cold spot supervoid appears to be significantly larger than what our models predict should be common in the universe. It's like finding a bubble in a piece of bread that's much larger than the typical air pockets you'd expect from the baking process. This suggests either that our models are missing something important about structure formation, or that the cold spot region has an unusual origin that goes beyond conventional cosmological processes. This is where the multiverse hypothesis becomes particularly compelling. If the cold spot represents the scar left by a collision between our universe and another bubble universe, then its unusual size and properties might be explained by the exotic physics involved in such an interaction. The collision would have occurred during or shortly after the inflationary epoch, when the fundamental forces and fields that govern structure formation were in states very different from what we observe today. Theoretical models of universe collisions predict that such interactions should create distinctive signatures in the cosmic microwave background. These signatures should include not only temperature anomalies like the cold spot, but also specific patterns of polarization in the CMB light and correlations between temperature fluctuations at different angular scales. Recent studies have begun to search for these additional signatures in the Planck satellite data. Some researchers claim to have found evidence for unusual polarization patterns in the cold spot region, while others argue that the statistical significance of these patterns is not yet strong enough to draw definitive conclusions. This is the nature of cutting-edge science. Researchers working at the very limits of what current technology can measure, using sophisticated statistical techniques to extract the faintest possible signals from incredibly noisy data. The search for evidence of the multiverse through CMB anomalies represents one of the most ambitious projects in modern physics. It's an attempt to use observational astronomy to probe questions that were once considered purely philosophical. Are there other universes? Can we observe them? What would it mean for our understanding of reality if we could? These questions connect to deep philosophical issues about the nature of existence and our place in the cosmos. For centuries, humans have grappled with questions about whether we are alone in the universe, but the multiverse hypothesis raises an even more profound question. Are we alone in reality itself? If the multiverse exists, then our observable universe, vast as it is, represents just one small bubble in an infinite ocean of realities, each potentially harboring its own forms of complexity, structure, and perhaps even life. The implications extend beyond philosophy into practical questions about the nature of physical law and the ultimate limits of scientific knowledge. If the multiverse hypothesis is correct, then many of the constants and laws that govern our universe, from the strength of gravity to the masses of fundamental particles, might be different in other bubble universes. This could help explain some of the most puzzling features of our cosmos, such as why the cosmological constant appears to be fine-tuned to allow the formation of stars and galaxies. In the multiverse picture, our universe doesn't need to be special or designed. It just needs to be one of countless realities where the physical constants happen to fall within the narrow range that permits complexity and structure. We observe these particular values not because they are fundamental features of reality, but because we exist in a universe where they allow observers like us to evolve and ask questions about the nature of existence. This anthropic reasoning, while controversial, provides a potential solution to some of the deepest puzzles in physics and cosmology. But it also raises new questions about the nature of scientific explanation and the limits of empirical investigation. If our universe is just one of infinitely many, each with different properties, then what does it mean to explain why our universe has the particular features we observe? The cold spot, in this context, becomes more than just an astronomical curiosity. It represents a potential window into the deepest questions about reality, a cosmic Rosetta Stone that might help us decode the ultimate structure of existence itself. Whether it ultimately proves to be evidence of the multiverse, a signature of exotic physics in our own universe, or something else entirely, It has already succeeded in pushing the boundaries of human knowledge and forcing us to confront the possibility that reality is far stranger and more wonderful than we ever imagined. As we continue to study the cold spot and search for other anomalies in the cosmic microwave background, we are participating in one of the most extraordinary detective stories in the history of science. We are using the faintest possible signals encoded in ancient light that has traveled for nearly 14 billion years to probe questions about the fundamental nature of space, time, and existence. The techniques we are developing for this investigation are themselves marvels of human ingenuity. Modern CMB experiments employ some of the most sensitive instruments ever built, detectors that can measure temperature variations smaller than a millionth of a degree while operating in the harsh environment of space. The data analysis requires computational resources that would have been unimaginable just a few decades ago, with researchers using supercomputers to run simulations of entire universes and compare them to observational data. But perhaps most remarkable of all is the conceptual leap that allows us to seriously consider the possibility that we might be observing evidence of other universes. This represents a fundamental shift in how we think about the relationship between theory and observation in physics. For most of the history of science, theoretical ideas needed to be directly testable through controlled experiments. The multiverse hypothesis challenges this paradigm by proposing that we might be able to test ideas about the fundamental structure of reality through careful observation of subtle patterns in the cosmos itself. This shift reflects the unique position that cosmology occupies in the hierarchy of sciences. Unlike laboratory physics, where we can manipulate variables and repeat experiments, cosmology deals with phenomena that occur only once, on scales so vast that we can never hope to replicate them. We have only one universe to study, at least as far as direct observation is concerned, and we can only observe it from one particular location and moment in its history. Yet this apparent limitation has become a source of unexpected power. The universe itself serves as the ultimate laboratory, a natural experiment carried out on the grandest possible scale. The cosmic microwave background represents the fossil record of the earliest moments of cosmic history, encoded in patterns of light that preserve information about physical processes that occurred when the universe was younger than the time it takes to bake a cake. The cold spot, viewed in this light, becomes a particularly precious piece of evidence. If it truly represents the signature of a collision with another universe, then it preserves information about events that occurred during the first fraction of a second after the Big Bang, when the fundamental forces of nature were unified and space and time themselves were emerging from the quantum foam of inflation. Understanding such events requires pushing our theories to their absolute limits, combining insights from quantum mechanics, general relativity, particle physics, and thermodynamics in ways that test the very foundations of our understanding of physical reality. The mathematics involved are so complex that even with the most powerful computers available, we can only explore simplified versions of the full theoretical models. Yet, despite these challenges, or perhaps because of them, the search for multiverse signatures in the cosmic microwave background has become one of the most active and exciting areas of research in modern cosmology. New observations are planned that will push the sensitivity of CMB measurements even further, potentially revealing additional anomalies or confirming the statistical significance of patterns already detected. Future space missions, such as the proposed Cosmic Origins Explorer, would map the polarization of the cosmic microwave background with unprecedented precision, searching for the subtle spiral patterns that some models predict should be left by gravitational waves generated during cosmic inflation. These primordial gravitational waves could carry information about the energy scales and physical processes involved in inflation, potentially providing crucial tests of different multiverse scenarios. Ground-based experiments are also pushing into new territory using networks of telescopes in locations ranging from the South Pole to the Atacama Desert to map the cosmic microwave background with exquisite detail. These experiments are particularly focused on measuring the polarization of the CMB, which provides complementary information to the temperature measurements that revealed the cold spot. The polarization of light carries information about the conditions in the early universe that produced the cosmic microwave background. Just as polarized sunglasses can reveal details about reflected light that are invisible to the naked eye, measurements of CMB polarization can reveal signatures of physical processes that leave no trace in temperature measurements alone. Some theoretical models predict that universe collisions should create distinctive polarization patterns in addition to temperature anomalies. These patterns would be extremely subtle, requiring measurements of extraordinary precision to detect, but they could provide the smoking gun evidence needed to definitively identify the cold spot as a multiverse signature. The challenge of detecting such subtle signals has driven remarkable advances in experimental technology. Modern CMB detectors use techniques borrowed from quantum mechanics and condensed matter physics, including superconducting devices that operate at temperatures just a few tenths of a degree above absolute zero. These detectors can measure individual photons of microwave light, counting them with precision that approaches the fundamental limits imposed by quantum mechanics itself. The data from these experiments generates computational challenges that push the boundaries of what even the most powerful computers can handle. A single all-sky map of the cosmic microwave background contains millions of independent measurements, each with its own associated uncertainties and systematic effects. Extracting meaningful patterns from such datasets requires statistical techniques that are themselves at the forefront of mathematical research. Yet perhaps the most remarkable aspect of this entire endeavor is how it connects the smallest scales of physics with the largest scales of astronomy. The quantum fluctuations that may have created the patterns we see in the cosmic microwave background occurred on scales smaller than the nucleus of an atom, yet they have been stretched by cosmic expansion to cover regions larger than clusters of galaxies. The cold spot, if it truly represents a multiverse signature, preserves information about interactions between universes that occurred when all of observable reality was smaller than the period at the end of this sentence. This connection between the quantum and the cosmic represents one of the deepest insights of modern physics, the recognition that the very largest and very smallest scales of nature are intimately connected through the processes that shaped the early universe. Inflation, the mechanism that may have created both the overall uniformity of the cosmos and the specific fluctuations that led to structure formation, is fundamentally a quantum process operating on cosmological scales. Understanding inflation requires treating space and time themselves as quantum mechanical objects, subject to the uncertainty principle and quantum fluctuations. This quantum nature of spacetime leads naturally to the possibility of eternal inflation and the multiverse, scenarios where quantum effects cause different regions of space to evolve in dramatically different ways, eventually becoming separate universes with potentially different physical properties. The mathematics of eternal inflation are complex and subtle, but they lead to clear observational predictions. If inflation occurred in our universe, it should have left specific signatures in the cosmic microwave background that we can search for with current and future experiments. The detection of these signatures would represent one of the greatest triumphs in the history of physics, confirming that our theoretical understanding of the quantum nature of space and time is fundamentally correct. But inflation also leads to profound conceptual puzzles that challenge our understanding of probability, causality, and the nature of scientific explanation. In eternally inflating multiverse models, every possible arrangement of matter and energy occurs infinitely often across the vast landscape of bubble universes. This raises deep questions about what it means to make predictions in such a scenario, and whether the scientific method can be applied to phenomena that occur on truly infinite scales. These philosophical challenges don't diminish the importance of searching for observational evidence of the multiverse. If anything, they make such searches more crucial. Only through empirical investigation can we hope to determine whether these theoretical ideas correspond to physical reality or represent mathematical artifacts of our current models. The cold spot, in this context, represents far more than a curious astronomical anomaly. It embodies the possibility that human beings, through careful observation and mathematical reasoning, might be able to probe the deepest questions about the nature of existence itself, We are attempting to use the tools of science to investigate whether our reality is unique or whether it exists as part of an infinite ensemble of universes, each as real and complex as our own. If we succeed in confirming that the cold spot represents evidence of another universe, it will mark a watershed moment in human history, comparable to the Copernican revolution or the discovery of the expanding universe. We will have learned that our cosmic horizon, vast as it is, represents only the smallest fraction of a reality so large and complex that it defies human comprehension. But even if the cold spot ultimately proves to have a more conventional explanation, the search for multiverse signatures has already transformed our understanding of the cosmos and our place within it. It has forced us to confront the possibility that reality extends far beyond the boundaries of direct observation, that the universe we see might be just one small part of a vast community of worlds. This investigation has also demonstrated the remarkable power of human reasoning and observational ingenuity. We have learned to read the subtle patterns in ancient light, to extract information about the earliest moments of cosmic history from signals so faint that they can barely be distinguished from noise. We have developed theoretical frameworks sophisticated enough to make specific predictions about phenomena that occur on scales from the quantum to the cosmic, and we have built instruments sensitive enough to test these predictions with extraordinary precision. The story of the cold spot is still being written. New observations and theoretical insights continue to refine our understanding of this mysterious region and its implications for our picture of the cosmos. Whether it ultimately proves to be a window into other universes or a signpost pointing toward new physics within our own reality, it has already succeeded in expanding the horizons of human knowledge and imagination. As we stand on the threshold of potentially revolutionary discoveries about the nature of reality, it's worth reflecting on the profound journey that has brought us to this point. From ancient observations of the night sky to sophisticated maps of the cosmic microwave background, from philosophical speculation about the nature of existence to mathematical theories of quantum spacetime, humans have gradually developed the tools and concepts needed to investigate the deepest questions about our place in the cosmos. The cold spot represents the latest chapter in this ongoing story, a mystery that challenges us to think more deeply about the nature of space, time, and existence itself. Whether we are alone in reality or part of an infinite multiverse, whether the laws of physics are unique or represent just one possibility among countless others, these questions touch on the most fundamental aspects of what it means to exist as conscious beings in a vast and ancient cosmos. In contemplating the cold spot and its implications, we are not just engaging in an abstract intellectual exercise. We are participating in the ongoing human endeavor to understand our place in the grand scheme of existence, to comprehend the nature of the reality we inhabit, and to push the boundaries of what it means to know something about the universe. The answers we seek may forever change how we see ourselves and our cosmic home. They may reveal that we are part of a reality so vast and complex that our current understanding represents only the first tentative steps toward true comprehension. Or they may confirm that our universe, remarkable as it is, represents the entire scope of physical reality, making us not citizens of a multiverse, but the sole inheritors of all existence. Either possibility fills us with wonder and challenges us to continue the search for understanding that defines us as a species. The cold spot, whatever its ultimate explanation, reminds us that the universe still holds profound mysteries, that reality may be stranger and more beautiful than we have yet imagined, and that the greatest discoveries may still lie ahead, waiting to be revealed through the marriage of human curiosity and the patient accumulation of knowledge about the cosmos we call home. In the end, perhaps the most remarkable thing about the cold spot is not what it might tell us about other universes, but what it reveals about ourselves, that we are beings capable of detecting the faintest whispers from the edge of reality, of asking questions that probe the deepest foundations of existence, and of finding in the vast darkness of space not emptiness, but the possibility of infinite wonder.